Okay, in the activity on Friday and the lesson yesterday, we started to talk about the concept of isotopes. And so today we're going to go in a little bit more depth about information having to do with isotopes of a particular element. And then we're going to talk about calculation known as average atomic mass that relates to the different isotopes of any particular element. Okay. And so if you look on your screen right now, we have the nucleus of three isotopes of carbon. There's carbon 12, carbon 13, and carbon 14. And so the first question I would ask you here is, what is the same between those three nuclei? What's the same in those three nuclei? If you could give me a direct message in the chat, I would appreciate it. Thank you, thank you. Thank you. Appreciate it. I love it when you guys give me so many responses so quickly that I can barely keep up reading it in the chat. That tells me that you guys are like focused in and engaged. Love it. So most people said either number of protons or the fact that they have 6 protons. That's exactly correct. It doesn't matter what isotope you have. If you have 6 protons, then the element is carbon. If you have 7 protons, the element isn't carbon anymore, then it's nitrogen. If you have 5 protons, the element isn't carbon anymore, then it's boron. So to be carbon, you have to have 6 protons, okay? Looking at those 3 diagrams, what things are different for those 3 nuclei that you see, carbon 12, 13, and 14? What's different? Thank you. Thank you. Thank you. Ooh, I like that. I like the way you added that slash with the second thing. That's different. Love it. Thank you so much. Okay, so we can tell by the diagrams. Appreciate everybody's participation. We can tell by the diagrams that the number of neutrons are different. So carbon 12 has 6. Carbon 13 has 7, and carbon 14 has 8 neutrons respectively. And of course, as a result of the number of neutrons being different, then that makes the mass number different too. That's why it's 12, 13, and 14. Somebody said the number of electrons are different. They could be. We can't tell that from this diagram because this diagram right now are just nuclei, but there is potential to have different numbers of electrons, but we definitely know that in these 3 isotopes, the number of neutrons and the mass number, those things are different, okay? And so when we look at isotopes, we have to consider that we have the same number of protons, but different number of neutrons, okay? Now, when you look at these mass numbers, 12, 13, and 14, one thing you'll notice when you take a look at the periodic table, and if you find carbon or any other element, you will see that that mass number there is not a whole number for most of these. Most of these are fractional or decimal numbers. And the reason for that is because anytime you have a sample of an element, it contains all the isotopes of that particular element. And those isotopes are not always in equal abundance. So if I took a look at a sample of carbon, I wouldn't necessarily have equal amounts of carbon 12, 13, and 14. I would have differing amounts of those different isotopes. And this number that you see on the periodic table is called the average atomic mass. And that average atomic mass is a weighted average of all of the isotopes in a sample. And when I say weighted average, I'm going to talk about what that means in just a couple of moments here. So you can see carbon's average atomic mass is 12.01. It's not 12, it's not 13, and it's not 14. It's a weighted average of all of those different isotopes that would be in a sample. Okay, so let's take a look at an example here. This is copper, right? So these are pure copper bars. And if we could zoom in on the individual particles that make up this copper bar, these copper bars, we would know that there would be only atoms of copper but there are different isotopes of copper, so they wouldn't all be exactly the same. And we might see something like this. So you can see, if you look in that diagram, that representation, there are some larger isotopes and some smaller isotopes. How many of the larger isotopes are there, and how many of the smaller isotopes are there in this particular diagram? If you could give me a direct message on that, that would be wonderful. How many large isotopes are there, and how many small isotopes are there of copper in this particular diagram? Appreciate the responses and the participation. Wonderful. Okay, so most people stated that there are 3 of the larger isotope and 7 of the smaller isotope, right? So I drew 10 circles total, which means that about 30% of the sample is the larger isotope and about 70% of the sample is the smaller isotope. And that would be true for any sample of pure copper in the world. If you had a sample of copper, it would be about 30% larger and 70% smaller isotope. Well, copper has 2 isotopes. There's copper 63 and there's copper 65. And you can see that it's not exactly 30%, 70%. It's about 69 and change and about 30 and change, but pretty close to 70 and 30% abundance of each of these isotopes. So it wouldn't matter if you had a small sample or a large sample. It wouldn't matter if you got your sample here in Grand Ledge or you got your sample somewhere else around the world. Every sample would have, on average, 70% copper 63 and 30% copper 65. And the difference, of course, is copper 65 has 2 more neutrons than copper 63, right? They both have the same number of protons, but there are 2 more neutrons in copper 65. Right, and of course, if you look up here, you can see that the weighted average is given to us on the periodic table. It tells us that it is approximately 63.55 what we call atomic mass units. So that's the weighted average of these 2 isotopes, which does tell us that the 65 is in lower abundance than the 63, because if it was perfectly 50-50, the average of 63 and 65, perfectly 50-50, would be 64. But you can see that this is less than 64. And the reason why it's less than 64 is because the isotope copper 63 is in greater abundance than copper 65. All right, so here are some common isotopes of elements that we work with regularly. So you can see that we do have copper 63 and copper 65 on there. Chlorine is one that we work with fairly frequently. So there are 2 isotopes. Chlorine 35 is in the greatest abundance, 75 to 76% abundant. And then the heavier isotope chlorine 37 is in lesser abundance, 24% approximately. Look at magnesium. Magnesium has 3 different isotopes. Some elements have 2, some have 3, some have 5. So some elements have many different isotopes. But magnesium is almost 80% abundant for magnesium 24, and then the other 20% is made up of magnesium 25 and 26, relatively speaking. Okay, silver is interesting, right? So if we look at silver, you will notice that the percent abundance isn't quite, but it's close to 50-50, right? So it's almost 52-48, 107 and 109. Well, if it was exactly 50-50, then the average would be 108. And I want to show you guys what the average actually is for silver. So I'm going to pull up my periodic table here. And if we find silver right here, you can see that the average is just under 108. It's closer to 107 because remember, 107 was about 52% abundant and 109 was about 48% abundant, but not by much. It's almost 108. And the reason why it's almost 108 is because silver has two isotopes that are approximately 50-50. They're not 50-50, but they are very close to being 50-50. Okay, so how can we calculate the average atomic mass? Well, the way that we would do that is by using this mathematical relationship where we would take the mass, the atomic mass of the first isotope, and multiply it by the percent abundance of that first isotope. And then we would take the atomic mass of the second isotope and we would multiply it by the percent abundance of the second isotope. Question for you guys, why does it say dot, dot, dot after that? What's the purpose of that? What's up with that? Dot, dot, dot. What does that mean? Why does anybody write that stuff? Thank you. I appreciate those responses. Right? So there could be more than two isotopes, right? And so if there are more isotopes, if there are three, then we're going to continue the same pattern with a third. If there's four, then we can continue the same pattern with the third and the fourth, and so on. So it goes as long as it needs to. There could be more isotopes. It shows that it continues, all of those things that you guys were saying there. Okay. Now, you guys know me, and you know that I like for anytime there's an equation, you guys to write the unsubstituted equation. But I know you, and I know you guys don't like to write a lot. And so I have a suggested abbreviation for this calculation for the unsubstituted equation step, and it looks like this. Atomic mass is equal to m sub 1 times percent sub 1 plus m sub 2 times percent sub 2, and so on. And so then you can just use this equation here in order to do the substitution instead of using this more lengthy, wordier equation that I know that you will not want to do. Okay, let's take a look at a couple examples. Okay, so this one says to calculate the average atomic mass of copper. Of course, we already know the average atomic mass of copper. That's not the point. We do want to just go through the process. There will be questions where you will be given isotopes of fictitious elements, made-up elements, where you'll have to calculate the weighted average based on those fictitious elements, right? By the way, I did want to make mention before we did this example. A good example of a weighted average is a grade that's calculated in a class that has categories, right? So if you think of like this class, for example, your homework and your tests are weighted differently. Your homework is 40% of your grade and your tests are 60% of your grade. And so what that means is I take the percentage of homework points you have and multiply it by 40%. And then I take the percentage of test points that you have and multiply that by 60%. That weights the test category heavier than the homework category. And so that's a good example of a weighted average as well, right? Just like all of these elements and their isotopes are not in equal abundance, right? It's not 50-50 between homework and tests. Tests are worth more, just like some of these isotopes are in greater abundance. Okay, so first thing that we would want to start with here, the equation. Atomic mass equals m, m1, sorry about that. I'm writing sloppy here. M1 times percent 1 plus M2 times percent 2, okay? If you calculate nothing and you do nothing else, you are going to get 1.4 writing that out. If you do not include that, you will lose 1 point, right? So this is going to be a 3-point question. There is your first point right there, okay? Second thing that we want to do is we want to substitute in the masses and the percentages. So for copper 63, the atomic mass is given to us. It's kind of a lengthy number, but we are still going to substitute that in. That is 62.929599 AMU. And then the percentage, we want to be careful with the percentage, right? So the percentage is a number out of 100, right? So I'm not going to multiply it by 69.17. I'm going to multiply it by 69.17 out of 100. And so just off to the side, 69.17 out of 100 means that we divide that number by 100, which essentially slides the decimal 2 places to the left. And so as a decimal, that's 0.6917. Okay, so when we have our percentage, you have 2 choices. You can either go 69.17% in your calculator, or if you don't want to hit the percent key, then you're going to slide that decimal over 2 places to the left, because a percentage is a number out of 100. And so that's going to be 0.6917. And then my second isotope for copper, copper 65, has an exact atomic mass of 64.927792 AMU. And again, 30.83 is 0.3, oops, sorry about that, 0.3083. Okay. If you don't have a calculator out right now, I am going to encourage you to go ahead and get out a calculator right now. So either a calculator or your cell phone calculator, or if you want to use the web, right, the internet for a calculator, that's fine as well. I see that I've got a question. I'm going to answer that question. And then I do want to point out something to you as well, right? So to earn this point, you are going to substitute as usual. You will notice that in the substitution, I have units of AMU, atomic mass units, okay? Question is, will the mass of the isotope be given to us on quiz questions? The answer is yes, right? Unless if it's asking you to calculate the average atomic mass, then it has to give you both the mass and the percent abundance. So the answer is going to be yes on that, okay? All right, if you would please take a moment and make the calculation. And with that calculation, if you could give me a direct message as to what you came up with, I'll give you just a second to do that. I'm going to do it myself. Thank you for your responses so far. I'm going to wait just a second here. Thank you for your responses. Okay. So as you guys are finishing up, I'm going to go ahead and finish up, right? So if I look at my calculator, right, I've got this big messy thing. It says, oops. It says 63.5456419. right? And so we want to express this with the correct number of significant figures, right? And so if I look here, this measurement has 4 significant figures, and this measurement has 4 significant figures. And so when we add them together, we are going to need to express our answer to 4 significant figures, which means that we're going to round here. And so then we are going to end up with 63.55, and the unit there is AMU, or atomic mass units. In order to get the full third point, we will need the unit, and then we will need those 4 significant figures. And so that is what we are looking for on that. Okay, right? And if we look at the periodic table and we find copper, 63.55, that's what it is. Let's do one more example. Okay, so again, with the example, this second example, we are going to start out with the equation. And it is asking for the atomic mass specifically of chlorine, right? And so there are 2 isotopes of chlorine. I'm going to ask you guys to go ahead and see if you can substitute the masses, the atomic masses, and then the percent abundance written appropriately, and then calculate the average atomic mass of chlorine to the correct number of significant figures. I'm going to give you a moment to do that. I'm going to do it too. Thank you. I'm going to go ahead and start my substitution. Okay, mass 1. And percentage 1. Mass 2. And percentage 2. All right, once I mash buttons on my calculator, I get 35.45273822. But we know here, hopefully we know that we want 4 significant figures, 4 significant figures. And so that is going to give me 35.45, and the unit is AMU. To earn all of the points in the second step, we need the units, AMU, Oh, I forgot it right here. I would lose a half a point on that. I did not include my unit there, which I need to. And that would give me my second point. And then on my third point, I've got 4 significant figures and the unit. And that would give me my third point there. Okay. Right. And so if we look on the periodic table, 35.45. Okay. How about any questions I can answer for you guys before I close up here for today? All right, so just a couple of things. Number 1, chapter 2, handout number 2 is due tonight. Number 2, I have assigned the average atomic mass handout today. It will not be due until Thursday night, but I do suggest that you get that completed as well as you can prior to Thursday, so that we can answer any questions you might have prior to that being due on Thursday night. And then tomorrow we are asynchronous, so there is no Zoom meeting. I am going to give you what's called a guided reading assignment, where you are going to be reading about the concept of nuclear radiation. So we've been talking about the nucleus of atoms, and now we're going to talk about nuclear radiation, things being emitted from the nuclei of atoms. And so I'm going to have you guys read about some different types of nuclear radiation, and then our lesson on Thursday, we'll talk more about the specific science of nuclear radiation as well. So there's going to be a guided reading assignment for you guys to work on tomorrow. Okay, that is it for today. I hope you guys have a lovely rest of your Tuesday, and I will see you again on Thursday. Take care.